In this video, we're going to have a quick look at an example of the type of three forces problem, the triangle of forces. We have three forces acting on an object, and we have to use a graphical method in order to find one of the forces that's not identified in the question. So what we have here, a very roughly drawn diagram, and it's a pump for a ship that's currently being lifted by two slings, one at a 40-degree angle above the positive direction of the horizontal with a 15.1 kilonewton force of tension in that sling, and the other on the left-hand side, a 50-degree angle above the negative direction of the horizontal, and there's an 18 kilonewton tension in that sling. And what we want to do is use a graphical method to determine the weight of the pump. And we can do this by using our triangle of forces. So in a triangle of forces problem, we're going to be drawing a scale diagram. Scale diagrams mean that each line we draw is on a scale, and I'll say what that means in a second. And every angle we draw is measured by a protractor, or in this case by my electronic whiteboard ruler, but you'll be using a protractor. So when I say a line's on a scale, it means that for every certain amount of force, and we can determine what that is in a second, for every certain amount of force there is, we will draw an equivalent length on our page. Now, an A4 piece of paper is about 20 by 30 centimetres or thereabouts, so none of your lines can be longer than 30 centimetres, and I would suggest that's quite on the long side. So we're generally trying to keep our lines to no more than about 10 centimetres, maybe a wee bit more than that. You've got room on your page for this, but think about how you're going to fit that on your page. So I've got two forces here that I know, 18 kilonewtons and 15.1 kilonewtons. So maybe an 18 centimetre line and a 15.1 centimetre line would be slightly on the big side. And maybe we could fit them in the page, but I think we want to try something smaller to begin with. But remember, if you're doing this yourself, draw it in pencil first of all, and if you can see clearly it's not going to work, well, you can adjust your scale. So rather than say, I'm going to make it 1 centimetre for every kilonewton, I'm going to say I'll make it 1 centimetre for every 2 kilonewtons. That means we take the number of kilonewtons in the force and divide it by 2, and that means the length of the line that matches that force will be half that force in centimetres. So that's the scale we're going to adopt. So I'll start off by saying what my scale is going to be. The scale is going to be 1 centimetre equal to 2 kilonewtons. So that means if I have a line that's 10 centimetres long, it represents 20 kilonewton force. So that's the first thing we have to establish. The next thing we're going to want to do is to start to draw these lines. Now, how we draw vectors like this, as we can see here, I'll do a very rough sketch here. We have three lines all coming out of a central point. This is our free body diagram. But when we draw our triangle of forces, we'll be joining them so that they go end to end like this to form a triangle. So each new force, each new vector will start from the arrowhead end of the previous vector. And I'll explain how I'm doing this as we go along. In a problem where we know two of the forces and one's unknown, we can choose either force to begin with. We'll always begin by drawing the two forces we know, but we can draw them in either order. So I could start off by drawing the 15.1 kilonewton force or the 18 kilonewton force. Both starting points will lead to the same solution for the problem. So there's no wrong way to begin if you pick one of those two. So for no particular reason, I'm going to pick the 15.1 kilonewton force. So how we would draw this on a piece of paper is first of all make sure we're drawing it in the right direction. So we can see in the diagram here that between a flat horizontal line on our page and going up and to the right, we've got an angle of 40 degrees. So if I were drawing this on a piece of paper, I didn't have my completely lined screen that I have here, I would definitely start off by drawing a very faint dashed line just to represent what horizontal is. And doing this in paper, I'll try and line this up with the bottom or top edge of my paper to make sure it's nice and parallel and keep things nice and neat for us, because neatness is going to be helps us out here. So let's have a look. Now what you would do now is you'd line up your protractor with this line, and you'd measure around 40 degrees starting from the right hand side. You'd be putting a dot in at the edge of your protractor and you'd draw a line through it, but I can't replicate that here. So what we'll do instead is I'll measure 40 degrees in the way that I can do so here, and that's using this ruler, which is quite fortunate. I want to make an angle of 40 degrees between this line, and I can pick any point on it because I've not started yet. Well, actually, let's make a little point for our starting point. You don't need to do this, but it can maybe help keep you right. So I'm going to put a little tiny little cross here. That'll be our starting point. So we've got an angle of 40 degrees here. That's up from the horizontal direction. And I said that I wanted to make my scale for every 2 kilonewtons 1 centimetre. So I take my kilonewtons, 15.1, and I divide it by 2, and that would give me 7.55. Now, that might be quite tricky to draw on a piece of paper, so if you can only draw it to 7.6, I mean, you could try and put it halfway between 2mm divisions, but 7.6 centimetres is close enough, because we're doing our best to be accurate here, but we're not aiming for perfection, because that level of precision just isn't possible. So we'll try and get something that represents 7.6 centimetres, 7.55. And I use little half divisions on my whiteboard ruler to represent centimetres. So for me, this is 1, 2, 3, 4, 5, 6, 7 centimetres. This takes me to the halfway point. I maybe just nudge my pen along slightly beyond this. On a ruler, you should be able to measure to exactly 0.1 centimetre, so 7.6. There'll be a marking in your ruler to draw that in. So make sure you do make use of that. But to 1 decimal place is what we're expecting in terms of accuracy. So what I've drawn in here is I've drawn an angle that's 40 degrees, and it's helpful for you to mark this, because it means if you go slightly wrong, I can see where you can still get marks. So this angle here is 40 degrees. And I've drawn a line which is 7.55 centimetres long, representing a 15.1 kilonewton force. And to show the direction here, I'm just going to put a little arrowhead in the end of this, like so. And this is where we'll draw our next line starting. So I'll just quickly highlight this. What I've drawn here, and I've circled in gold, is a representation of this sling here. But I've taken it from the starting point. What we're doing now is we're going to be taking this line, I'm highlighting in gold, and we're sliding it up so that it comes out of this point here instead. So it's still going to be in the same direction. It's going to be the same size, but now rather than starting from the middle, it's going to be starting from the end of the first line we've drawn. And this is because in a static system, if we add all of our forces together like this, they'll come back to the starting point, and that will give us a way of finding the value for W. So I'll clear these markings off the diagram just now and show you what we're going to do next. So again, I can do this directly in the whiteboard, but I think on a bit of paper you want to do this as well. You want to take your ruler, and just so that we're being nice and accurate here, we can draw a little dashed line just touching the end of our first vector. And this is going to give us a position to measure our next angle from. Because if you remember what I said at the beginning, this second vector, so the one we're looking at just now, I've just circled that in gold on the left-hand side there, that is coming up this way, and the angle is going to be 50 degrees, and we'll make the line the right length in proportion with the force. So let's measure this precisely. So again, you measure a 50-degree angle with your protractor. Again, you start on the left of your protractor this time and come round 50 degrees. I'm able to use the whiteboard ruler and align it up like this. I'm just going to check before I start drawing here that I've got enough room to draw this in. And I'm slightly short on room here, so I'm going to do a little bit of cheating. I'm going to move my text that says scale. I'm just going to shift it over here. And that's why I really do suggest drawing this in pencil. You can save yourself a lot of redrawing. So I've got my angle of 50 degrees measured. I line it up, so my starting point is the arrow from the first vector. So we're following a path. We've come up this arrow. Now we're going to head off in this direction, and it's an 18 kilonewton force, but that's easy to draw on any ruler. We know it's divided by 2. It gives us a 9 centimeter line. So I'll draw 9 centimeters along here. And that looks pretty good to me as 9 centimeters. Other things I could have marked, and I could have actually said that this was a 15.1 kilonewton force. I might have also said how much it was in centimeters, but we'll get that from measuring the diagram. This is a 50-degree angle here. This is an 18 kilonewton force. I will do a little arrowhead in here to show that this line is pointing this way. And now for the final piece. So we know what direction the weight heads in. It's a weight always points directly downwards. It's just the gravitational pull of the Earth. So it's looking pretty good in our diagram. It looks like that, and I'll put the final line in a different color just so that we can see what we're trying to find here. It looks pretty much like we're going to get a direct straight line. I mean, mine's maybe slightly off, but I think that's close enough to say it's a directly straight line down there. If you're doing a problem with this, it's not perfect, so there's a slight angle, then just go with it. Because it should be a completely straight line, but tiny inaccurate measurements are going to throw you off. If your line was sloped like this or like this, we're maybe a little bit too far out. If you end up having a line that looked a bit like this, for example, it could be forgiven in the marking. You wouldn't lose marks for that because it's so something a couple of degrees off. There's not one precise, this is how wrong you can be and get it right, but sometimes we will be slightly off with these things. But we should be, and you should know this from the question, aspiring to a completely straight line here at the end. Unfortunately, it appears to have pretty much got that. So we complete our triangle of forces, because remember, because this scenario is that the pump is suspended, it's not moving up, it's not moving down, it's not moving side to side, it's just sitting there waiting for maybe to be either for force to be removed or applied to lower or raise it, but currently it's sitting still. We should come back to our starting point. This tells us there's no overall direction, it's just completely balanced. And so I'll draw this final line in here. And for completeness, I'll put a little arrow on it. We have no angle to measure here because if we're drawing a line straight up and down, we just make it parallel to the side of our paper and make a completely straight line. And of course, this is our force W, which we haven't worked out yet. This takes us back to why we do any of this to begin with. The reason is because now we can measure this line using our ruler, and whatever value we get in centimeters, we multiply it by 2 using our scale, and that will tell us the weight in kilonewtons. So looking at this, I'm counting 2, 4, 6, 8, 10, maybe 11 point. It looks like you're short of 12, so I'm going to call it 11.9 here. You can obviously be a lot more precise. And so you could write something simple as line for vector W is 11.9 centimeters. That's equal to 2 times 11.9, which is 23.8 kilonewtons. So that'd be your answer. Now, I don't know exactly what it's a definite correct answer to this. You can calculate using trigonometry, but certainly this answer would be accurate enough in a question like this. So the key parts are identify a suitable scale, measure your angles accurately, convert any forces using the scale, and do your best to draw these things in accurately with your ruler. And then we add the vectors tip to tail. So we draw a line, and then the arrowhead of that line, we draw the next one. And in a problem like this, where there's one unknown force, we draw in the 2 that we know first of all, and that leaves us with an empty side of our triangle, which should hopefully be pointing in the right direction. And the length of that final line is the solution to the problem. So for any questions you encounter like this approach will always work.